In any standard single-variable calculus class, students learn that continuous functions drawn on a closed interval are predictable. They are well-behaved. They do not suddenly escape to infinity or vanish off the page. This observation is formalized early on as the extreme value theorem. A continuous function on a closed interval will always attain an absolute maximum and an absolute minimum. But taking that rule for granted skips over the mechanics of the mathematics. What specific property of the function forces it to stop growing and turn back around? Visualizing a line on a coordinate plane provides intuition, but masks the underlying engine. The geometry of the graph emerges from specific topological rules. The constraint of compactness enforces this boundary behavior. To understand how this works, we move away from the familiar one-dimensional number line and look at general, abstract metric spaces, typically denoted as x and y. In real analysis, we strip away the coordinates. We stop looking at lines and curves, and instead look at how a function maps entire sets of points from one abstract space to another. The core property of a continuous mapping is that it preserves proximity. Points that are close together in the input space remain close together in the output space. However, continuity alone does not prevent a set from stretching out infinitely. That requires compactness. Compactness is a specialized property that preserves the finiteness of a space. It guarantees that if a set can be covered by an infinite collection of open neighborhoods, it can always be fully enclosed by a finite subselection of those same neighborhoods. When you apply this property of compactness to a starting domain, it acts as a rigid structural cage, preventing the continuous function from exhibiting escaping behavior in the output. To prove the extreme value theorem, we must first prove a much broader master theorem, showing exactly how the property of compactness survives the journey through a continuous mapping. This brings us to Theorem 4.14 in Rudin's Principles of Mathematical Analysis. It states the continuous image of a compact space is, itself, compact. The proof begins by covering the image in the target space with an arbitrary, potentially infinite collection of open sets. The topological definition of continuity does the heavy lifting here. By pulling those target sets backward through the function, we guarantee that the resulting pre-images are open sets that successfully cover our starting domain. Since the domain is compact, we reduce this infinite collection to a finite number of sets covering the input. By pushing this finite collection back forward through the function, we demonstrate the target set is covered by a finite subcollection. The structure holds. This topological fact is the mathematical foundation for all bounding behavior. We can now take this abstract spatial proof and bring it back down to the territory of real numbers and Euclidean space. Theorem 4.15 acts as our translator. It applies the Heine-Borel theorem to show that in Euclidean space, being compact means a set is both closed and bounded. Because the image is bounded, the output of the function is strictly capped. There is a hard numerical ceiling it cannot exceed and a hard numerical floor it cannot drop below. But boundedness alone doesn't mean the function actually touches that ceiling. For that, we look at Theorem 4.16 and the second requirement of compactness. The image must be a closed set. Closed sets contain all their limit points. This means the absolute highest theoretical boundary, the supremum, and the lowest boundary, the infimum, are physically contained within the output set. Consequently, there must exist specific input points, P and Q, inside the domain where the function strikes these extreme values. The extreme value theorem represents a direct manifestation of a compact set mapping into real numbers. To see why this structural constraint is necessary, we can look at what happens to continuous functions when the domain fails to meet the criteria for compactness. Theorem 4.20 outlines the failure modes. First, if the domain is unbounded, a simple continuous function like f of x equals x remains unbounded, traveling endlessly alongside the domain. Failure can also occur on a domain that is bounded but not closed. If a boundary point is missing, a continuous function can use that precise omission to construct an asymptote. It scales that asymptote to infinity, escaping any bounds while remaining perfectly continuous. Even if the function remains bounded on a non-compact set, it may fail to attain a maximum. As shown in equation 22, it can approach a supremum asymptotically, never finding an input that actually reaches the top. Without both components of compactness, both boundedness and closeness, The property of continuity lacks the geometric strength to prevent escaping behavior. This topological necessity extends beyond forward mappings. Compactness preserves structure when functions run in reverse. Rudin illustrates this with example 4.21, mapping the half-open interval from 0 to 2 pi onto a unit circle. The forward mapping operates flawlessly, taking the straight line segment and wrapping it into a continuous two-dimensional circle. However, the starting interval is missing the 2 pi endpoint. It is not compact. Because of this missing constraint, the inverse function fails. Attempting to unwrap the circle back into a straight line violently tears the space at the coordinates 1, 0, destroying continuity. Compactness provides the required structural glue for true bicontinuous topological equivalency. Compactness acts as the definitive control mechanism over continuous functions. It restricts where they can go, how far they can stretch, and whether they can be reversed. The logic holds. Continuous images of compact sets remain compact. That compactness guarantees bounded outputs, and the closed nature of the set ensures those absolute boundaries are struck perfectly. The interplay between continuity and compactness provides the rigorous framework for classical real analysis. The interaction between these two concepts remains a central pillar of the subject. If you want more structured explanations from texts like Rudin, don't forget to like, subscribe, and continue your journey into higher mathematics. The next time you observe a simple curve on a graph and identify its peak, you recognize the specific topological cage holding it there.